Have you ever wondered what antimatter is? It's not science fiction, but a real and fascinating concept in physics. Imagine looking into a mirror, but instead of seeing a reflection of yourself, you see a version composed entirely of antimatter. Antimatter is essentially the mirror image of regular matter, made up of antiparticles with properties opposite to those of normal matter particles. Every subatomic particle, be it an electron, a proton, or a neutron, has a corresponding antiparticle. These antiparticles possess the same mass but have an opposite electrical charge and other properties. However, antimatter is a rare occurrence in nature. Why? Well, when a particle meets its antiparticle, they annihilate each other, converting entirely into energy. This annihilation makes the existence of antimatter on Earth incredibly rare. So antimatter is not just a creation of science fiction, but a real, albeit elusive, part of our universe. But what exactly makes up antimatter? It's all about antiparticles. Picture the world of subatomic particles, electrons, protons, neutrons that make up the matter we're familiar with. Now imagine a mirror universe where every one of these particles has a counterpart, a doppelganger with the same mass but opposite electrical charge and other properties. Welcome to the world of antiparticles. The antiparticle of an electron, which is negatively charged, is a positron, carrying a positive charge. The antiparticle of a proton, which is positively charged, is an antiproton carrying a negative charge. These antiparticles band together to create what we call antimatter. But here's the catch: when a particle meets its antiparticle, they annihilate each other, disappearing in a burst of energy. Quite the dramatic ending, don't you think? So, antiparticles are like the alter egos of normal particles, same in mass but opposite in other qualities. Antimatter sounds intriguing, doesn't it? But how do we create and store it? Let's delve into the fascinating world of antimatter production and containment. Scientists have developed a method to create antimatter using high-powered devices known as particle accelerators. These machines propel particles at nearly the speed of light, colliding them together in a high-energy environment. This process generates a slew of particles and antiparticles, including our coveted antimatter. However, the production of antimatter is an intricate and costly process, yielding only minuscule amounts at a time. Now, creating antimatter is one thing, but storing it, that's another beast altogether. Remember that antimatter and matter are not exactly the best of friends. When they meet, they annihilate each other, releasing a burst of energy. This makes containing antimatter quite the challenge. Antiparticles are naturally repelled by normal matter, which makes conventional storage methods ineffective. To contain antimatter, scientists use what's called a penning trap, a special container that uses a combination of electric and magnetic fields. These fields prevent the antimatter from coming into contact with the matter that forms the walls of the container. This way, the antimatter can be stored safely without causing a mini energy explosion. Creating and storing antimatter is no easy task, but scientists have managed to do it, albeit in minute quantities. The realm of antimatter is a testament to human ingenuity and our relentless pursuit of understanding the universe's mysteries. Despite these challenges, antimatter has some potential applications that could revolutionize certain fields. Let's dive into a few of these theoretical applications. First, imagine a spaceship propelled by antimatter. Yes, you heard that right. Antimatter could be used in highly efficient propulsion systems for spaceships. This is because the complete annihilation of fuel and antimatter would convert all mass into energy according to Einstein's famous equation E equals mc squared. This would provide a level of efficiency that is currently unthinkable with our existing propulsion technologies. Then there's the potential for advanced medical imaging. The positron, the antiparticle of the electron, could be used in imaging techniques that are even more sensitive than current methods. One such technique is positron emission tomography, or PET scans, which are used to observe metabolic processes in the body. The use of antimatter could enhance the sensitivity and accuracy of these scans, providing better diagnostic tools for medical professionals. It's important to note, however, that these applications are largely theoretical at this stage. The production and containment of antimatter are major hurdles that we need to overcome. But the potential benefits are so extraordinary that they continue to drive research in this field. While the widespread use of antimatter remains a distant prospect, its potential applications keep scientists intrigued and driven to explore further.